All right, that's probably not enough time to have gotten through them all, but let's go through them anyway. And I think these first two we can just fit on here, but the last three we will have more people for. So what's the derivative of e to the x cubed plus sine of x? Well, I'm thinking of that as e to the stuff. I'm really just thinking of the chain rule like all the time when I'm taking derivatives. And the derivative of e to the x is e to the x. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative of e to the x cubed plus sine x is e to the x cubed plus sine of x times the derivative of that stuff, which is 3x squared plus cosine of x. It's also worth mentioning here that if somebody asked you what the antiderivative of e to the x cubed plus sine x times 3x squared plus cosine x was, you could say it's e to the x cubed plus sine of x, right? Definitely going back this way. That is the antiderivative. And you slap on a plus c, of course. All right, here's one that you may have forgotten from 21A. It's one that we don't see all the time, but it certainly comes up relatively semi-frequently. The derivative of 6 to the x is kind of like taking the derivative of e to the x. The derivative of e to the x is e to the x. The derivative of 6 to the x is almost 6 to the x. So there's a little bit more. There's a, in fact, it's on that rule sheet that I just handed you all. It's 6 to the x times the natural log of 6. And in fact, it even works for e. Just as a reminder, the derivative of e to the x, you could really think of it as e to the x times the natural log of e. It's just the natural log of e is equal to 1. So whenever your base is something other than e, when you differentiate, you end up multiplying by the natural log of that base. And we'll come back to that in a moment. Yeah, in a moment. So what about these other three questions? Asking us, are these integrals equal to these other functions? So at this stage, we don't have the ability to integrate any of these things yet. We will certainly learn how to use, but I think all these are either u substitution or integration by parts problems. We'll definitely learn those methods of integration a little bit later. For now, if someone ever asks you, is this integral equal to this function? You can check that by taking the derivative of the function. So when we want to answer the question, is the derivative of the natural log of x, is the antiderivative of the natural log of x equal to x times natural log of x minus x plus c? The way we check that is, and I guess I'll write it down again so that the paper makes sense when I post it later. We take the derivative of this. So we're going to take the derivative of the thing that's the antiderivative, or the candidate for the antiderivative, because maybe it's not actually the antiderivative. It is, but you know, it's good to speak generically. So we take the derivative of x times natural log of x minus x plus c. Here we have to use the product rule. So the derivative of x times natural log of x is going to be the derivative of x, which is 1, times the other piece, which is natural log of x, plus x times the derivative of the natural log of x, which is 1 over x, minus the derivative of x, which is 1, plus the derivative of c, which is 0. And then if we simplify a little bit, we end up with natural log of x plus 1 minus 1, which equals the natural log of x, which is the thing that we were supposedly taking the antiderivative of. So yeah, this checks out. The answer here is a resounding yes. The integral of that is equal to that because the derivative of x natural log of x minus x is equal to natural log of x. So I really can't stress enough how important this relationship between derivatives and antiderivatives is, right? If you do an antiderivative and then take the derivative of that, you should get back to the function you started. They always undo what the other one does. Let's look at the next example, which was, is the antiderivative of 2x cosine x equal to x squared times sine of x? So we're going to check, is the antiderivative of 2x times cosine of x dx equal to x squared times sine of x plus c. And we're going to check in the usual way, which is that we're going to take the derivative, well, I should say the usual way at this stage. We're going to take the derivative of x squared times sine of x. By the way, for those of you on Zoom, if you have a question, if you want to write something in the chat, go ahead. If I don't see the thing in the chat, you can like try raising your hand or unmuting yourself and saying words. Either way is fine. Just, yeah, but if you have questions, don't hesitate to write them in there, ask them, whatever. So let's see here. So I'm going to take the derivative of x squared times sine of x. And just like the previous problem, I'm going to have to use the product rule. The derivative of x squared times sine of x is the derivative of x squared, which is 2x times not the derivative of sine of x, right? Just sine of x alone. Plus, now you leave the x squared alone, times the derivative of sine, which is cosine of x. And that is definitely not looking like 2x times cosine of x. So the answer here is definitely no. The antiderivative of 2x times cosine of x is not equal to x squared times sine of x. This problem is kind of meant to be a little misleading, because if you were doing this the wrong way, if you just anti-differentiated 2x and got x squared, and anti-differentiated cosine x and got sine of x and then multiplied them together, you might think it was right. But it's very, very important to know that you can't just anti-differentiate two functions and multiply the results together. It doesn't work. I will tell you, and you can check on your own sometime. I wrote this down somewhere. I guess I can just do it again real quick, but there we go. I will point out that the antiderivative of 2x times cosine of x dx is equal to, 2x times sine of x minus and minus, so plus 2 cosine of x plus c. You should check this on your own later, or right now if you have time. But that's definitely, yeah, totally. Yes, definitely. I left it in there to be very suggestive of the integral 2x being x squared, but you're totally right. We can definitely pull the 2 out from here and from our answer over here. Let's look at the last one that I wrote down here, which was, is the integral of 7x to the 6th over x to the 7th plus 1 dx equal to the natural log of the absolute value of x to the 7th plus 1? Let's see. I will tell you, when you take a derivative of the natural log of the absolute value of everything, you kind of just ignore the absolute value. So I'm going to just kind of pretend like it's not there. So the derivative of the natural log of the absolute value of x to the 7th plus 1 plus c. Well, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Plus the derivative of c is 0. So yeah, that does work out to be the thing we thought it should be. Cool. Questions about any of the things I said here or did here? Yeah.
Is that one with the integral of 2x times cosine of x dx, is that integration by parts?
That would solve that way using integration by parts, yes. Typically, it's often the case when you have functions kind of multiplied together and you can't just integrate it right away. You often end up using integration by parts, but we will definitely talk at length about integration by parts when we get to, I think it's section 6.1 in your textbook. So yeah, it's a little ways off, but we will be there before you know it. The one function that I wanted to address on this page is the exponential function 6 to the x. So let's look at that for just a minute, and then we'll move on to talking about approximating the area under a curve. So yeah. So we said just now that the derivative of 6 to the x is equal to 6 to the x times the natural log of 6. And more generally, for any positive base that's not 1, you can say that the derivative of, I guess I should use the same notation as the handout, might as well be consistent here. Sure, the derivative of a to the x is equal to a to the x times the natural log of a, as long as a is positive and not equal to 1. And that's just a general derivative rule that we've used before and comes up every once in a while. This also lets us know how to find the antiderivative of something. So I'm going to remind you something I said last class, which is that if you want to integrate or anti-differentiate something like, let's pick something fun, like, let's do that. Let's do 5x plus 1 to the 99th power. It seems like it might be terrible, but it's really not. So we're looking, let's actually make it even easier. Let's make it 100 times 5x plus 1 to the 99th power. So a good guess, but a wrong guess. But a good guess would be 5x plus 1 to the 100th power. Why is that a good guess? Well, if I take the derivative of something to the 100th power, the 100 comes down, this stays the same, and you get the 99th power. But what am I forgetting about? I would say the 5 or the 5x plus 1, right? We're forgetting about the derivative of this inside power. We're forgetting about the chain rule. So if I were to differentiate 5x plus 1 to the 100th power, I would get 100 times 5x plus 1 to the 99th power times the derivative of the inside, which is 5. So the problem is, if the antiderivative of 100 times 5x plus 1 to the 99th is going to equal a thing, its derivative should equal the original function I antidifferentiated. But I'm off by this factor of 5. So I'm going to divide by 5 to make up for it. I'm going to throw out a 1/5 or division by 5 right there, and a division by 5 right there, and a division by 5 right there. So again, I want to emphasize, if your answer is off by a constant multiple, it's really easy to fix. If you can see that this antiderivative, and when you differentiate it, you're going to be off by a factor of 5, divide by 5. The same thing is true for this kind of exponential function. If you are trying to find the antiderivative of 6 to the x, well, a good but wrong guess would be 6 to the x. And the reason it's a good guess, aside from I know for an answer, is 6 to the x is a lot like e to the x. And the antiderivative of e to the x is e to the x. So it makes sense to say, well, it's probable that the antiderivative of 6 to the x would be something like 6 to the x. The problem here is that if you take the derivative of 6 to the x, you end up multiplying by a natural log of 6, which I want to restate one more time is a constant. I don't know what it is. I really don't know what it is. It's like, I don't know, 1.85, I think. I'm really just guessing. It could be totally different than that. But it's definitely something that never changes, right? Natural log of 6 is always the same number every time you put it into a calculator. And if it's a constant, it means you can multiply or divide by it without really messing anything up. So since I know that the derivative of 6 to the x is equal to 6 to the x times the natural log of 6, but I want the derivative of my thing to equal just 6 to the x, I'm going to throw in a 1 over natural log of 6. Because it's totally fine to divide by a constant. And then these end up canceling, and you end up getting just 6 to the x. So what we need here is the antiderivative of 6 to the x to be 1 over the natural log of 6 times 6 to the x plus c. Or as people like to write, 6 to the x over the natural log of 6 plus c. And that's kind of the last antiderivative rule that we kind of already should know because of differentiation, but I didn't talk about on Monday. So now if you look at that list that I gave everybody in class, you'll see that all the rules we talked about are on there. Some of them are a little more general, like they throw in a constant k a lot of the time just to kind of be general about it. But those are all rules that we mentioned at some point in class yesterday. Or was it on Monday? Sorry. So just to kind of go along with this for a second, in general, if you're finding the antiderivative of a to some power, that's not the right way to say that. The antiderivative of a to the x is not just some power, it's very specifically a to the x. The antiderivative is going to be a to the x divided by the natural log of a. That's a constant. And again, it should be clear, but I'm going to say it anyway, that a must be greater than 0 because you can't take the natural log of a negative number. And a also can't be 1. Very specifically here, because the natural log of 1 is equal to 0, and dividing by 0 would be a problem. All right, so we will definitely revisit these rules as we start talking more and more about integration, the fundamental theorem of calculus, and all that kind of jazz. But I will say at this juncture, there's an expectation that you are able to do these antiderivatives pretty straightforwardly. Right? These shouldn't take too much effort. Maybe some effort to do the ones that are more complicated, but the ones that are all on that list, that's definitely a list you should look at. Make sure you know them. If you have questions about them, come see me during office hours. Happy to talk about them more and more and more and more. But we definitely should move forward because there are more things to talk about. So do I want to do that example? Kind of, yeah, sure. Maybe I'll. So I've got a couple different examples I could do. Let's talk through this example. Yeah, not. Sorry, I'm debating with myself if I want to write things down or just show you the pictures. Let me show you the pictures, and I'll write down the next one because this one's already written down. And I think it's good. So let's take a look here, and I'll do this. Sure. So this first thing we're going to do or talk about doing is estimating the area under the function f of x equal to the square root of x on the interval from 0 to 16 using a regular, which just means all the partitions are equal length of 4 rectangles. And we're going to do this we're just going to look at this in a couple different ways so we can talk about what's happening here. But the math is always kind of a little bit gross. So the idea is we're taking this curve, we're dividing up the interval from 0 to 16 in this case, and you can pick any number. 4 is a very common choice because it's big enough that you feel like you're doing something, but it's not so big that it takes a lot of effort. But like when you get to like 6 or 8 or 10, it starts to get really, really gross. We're going to take this interval from 0 to 16, divide it up into 4 equal subsections. So each subsection has a length of 16 divided by 4, which is 4. And then for each of those sub-intervals, we're going to estimate the area under the curve using a rectangle. And we're going to estimate using rectangles located at different spots, meaning in this first iteration here, for each subinterval, we're going to use the right endpoint of that subinterval to give us the height of the rectangle. So for this first one, the right endpoint is 4. And if I plug in 4, I'm going to get f of 4, which happens to be 2, because it's the square root of 4. So the area of this first rectangle is the base delta x, which is 4. There's my delta x over there. It's always going to be your total interval length divided by your number of subintervals, which in this case happens to be, and I'm writing the same thing down. It happens to be 4. So this rectangle's area is the base 4 times the height f of 4. This rectangle's area is also the base 4, but now we're plugging in the right endpoint, which is 8 to get the height, and f of 8 is going to be the square root of 8. And then the third one, we're going to plug in 12 to get the height. The fourth one, we're going to plug in 16 to get the height. So in this particular iteration of this, we are using the right endpoints to get the heights of the rectangles. But that's not the only way to do it. It's usually if someone's going to do it, that's the way they're usually going to default to because it's usually the easiest way. But there's 5 other ways we can do this as well. I will also mention that this choice happens to give us what is called the upper sum as well. Meaning in each interval, we happen to be picking the point that gives us the highest value of the function. It's really just because this function happens to be an increasing function. But we'll see another example of this in a minute.
So we could also do more, right?
Right. Well, so I would say we could also do left. And in this particular example, left and lower happen to be equivalent, and right and upper happen to be equivalent. But I'm going to show you another example in a little bit here where they're not always the same, which is good to know. So if you do this calculation, you get these various things. You get 4 times the square root of 4 plus the square root of 8 plus the square root of 12 plus the square root of 16. And if you plug that into a calculator, which is not particularly exciting, you end up getting about 49.17. Hurrah. That would be an upper, or I should say an overestimate of this function. It's also the upper sum, as you know. And we can do this using right endpoints, or we can do it using left endpoints. If we do left endpoints, it's going to look more like this. So now my first rectangle feels kind of silly. It's got a height of 0, which, okay, fine. Sometimes it's going to happen. Really, when I looked at this one, I thought about, well, I'm really going to have the same numbers, except one of them is going to be different. My left endpoint for the second rectangle is going to be 4. So I'm going to get f of 4. For my third rectangle, it's going to be 8. So I'm going to get f of 8. For my fourth rectangle, I'm going to get 12. So I'm going to get f of 12. So I'm really losing this square root of 16 and gaining a 0. So when I do this, my area is approximately, well, the area of this rectangle is 4 times f of 0. The area of this rectangle is 4 times f of 4, 4 times f of 8, 4 times f of 12. And you add those together, you get about 33.17. And I think we can all see it's definitely an underestimate, right? I'm missing all of these little areas right here. So I'm an underestimate by probably quite a bit. Here I'm an overestimate by these amounts here.
For underestimates, we go up to.
I'm sorry.
For underestimates, do we go up till 9, I mean, n minus 1 over n?
Well, yeah. So if you, well, I would say I'm going to go back to right and left. So it's not that it's not that using right endpoints is always an overestimate.
Yeah.
But if your function is increasing, then it will always be an overestimate. And if your function's increasing using left endpoints will always be an underestimate. And you're right. If you're using right endpoints, you always start at the first one instead of the 0th one and end at the nth one. If you're using left endpoints, you'll start at the 0th one and end at the n minus 1 one.
So my professor uses the words upper and lower.
We're-
endpoints.
Yes, we're endpoints.
Yeah. Does that mean, like, when he says upper, no matter if it's increasing or decreasing, does that just mean the higher f?
It means, so if you're trying to find the upper sum, which again, we're going to talk about in just a second, it means you want to pick the point, and it might not be the left or the right. It might be somewhere in the middle that gives you the highest value of the function. Now, I looked at Hunter's homework, and all of the upper ones happen to be either increasing or decreasing functions. So it's kind of the same either way, but that's not always necessarily going to be the case. It probably will be in our experience because we try to make it not terrible, but we'll see an example where that's not the case today. Yeah, today we've got enough time. So just to go on with this for another moment, we could also use midpoints. We wanted to. So instead of using 0 and 4 and 8 and 12, or 4 and 8 and 12 and 16 as our left or right endpoints, we could use the midpoint of each subinterval, 2 and 6 and 10 and 14, and plug in those values to your function, which is still the square root function, to get heights being square root of 2 of, I think that's right there. I'll write them down here. Square root of 2 plus square root of 6 plus square root of 10 plus square root of 12. And that would give you an estimate using, sorry, let me say words here, using midpoints, and it's going to be approximately 43.07. Now, from the picture, it's not really obvious whether it's an overestimate or an underestimate. I know it's a slight overestimate because I've done the actual antiderivative and used the fundamental theorem of calculus to find the area. Okay. Yeah, and then finally, really you can actually use any point in the interval. So usually we default to using right endpoints, sometimes left endpoints, sometimes midpoints. We almost never pick just any points we want, right? You can make up your own partition with nice values like 1, 4, 9, and 16. There's a partition that has, it's non-regular, right? Because each interval length isn't the same as each other, but this is totally an estimate of the area under the curve. This first rectangle has a base of 1, a height of 1. The next one has a base of 3 and a height of square root of 4, base of 5, height of square root of 9, base of 7, height of square root of 16. For an area of, we'll talk about that in a minute, 1 times 1 plus 3 times 2 plus 5 times 3 plus 7 times 4. So about 50, which is giving you a big overestimate.
Does using non-regular partitions make it more accurate depending on the concavity?
You had me at no until you said concavity, and then I don't know. The reason for using a non-regular partition often is to make the values that we're plugging in easier. So that's why you would make this choice here, because these values are easy to plug into the square root function and get nice values out. But it's still definitely giving us an overestimate. Now, the thing that's not going to end up mattering in the end is whether it's an overestimate or underestimate. If you make all of the rectangles super duper narrow, then your overestimate or your underestimate becomes infinitesimally off, because you're just having this super narrow rectangle and the amount you're off by is just this tiny little sliver. And that's kind of the idea moving forward, is that you're going to let the number of partitions or the number of subintervals get larger and larger and larger. So I should point out also there's this thing called the norm of the partition. So the partition is the width of the widest subinterval. So when we talk about, and this is going to be a little bit later, we're still not quite there. When we talk about defining the area under the curve, defining the integral, the idea is usually to let the width of the widest subinterval get smaller and smaller and smaller. We want all the rectangles to get narrower and narrower and narrower. Try saying that again, narrower, so that our approximation gets more and more accurate. Okay, let's look at another example. That's a little back up here. Cool. I'm gonna make sure everyone, Zoom got the attendance form. Okay, there you go. So, and I'll definitely, so in case you're unaware, these are grant notes that I was using there. I will definitely post those as well so you can see them. So you can see that example, but now I'll use my own example here, which I have. It's great. It just takes time to write all the pictures down, which I'm sure you're aware of. So let's look at another example of estimating the area under a curve. That's not the right one. You're the right one. Cool. So let's estimate the area under, what have I got here? F of x equal to 5x minus x squared on the interval from 0 to 4. And again, we're trying to make our life easy. Let's make that a little more in focus, maybe. Yeah. And we're going to use n equal to 4 subintervals. And we'll start off first using right endpoints. It is worth noting, you could totally do this problem without drawing a picture. You could definitely divide up your interval from 0 to 4 into 4. In fact, I could maybe do without drawing a picture, but not in a way that's helpful to you. So I'm certainly gonna draw a picture, but I will do less picturing at first here. So if I go from 0 to 4, I will fill in the picture, so don't worry. But you could say, well, I know how to find areas of rectangles using right endpoints. The area is going to be approximately, well, the area of the first rectangle, I guess I should, okay, fine. Sorry, I maybe jumped a little bit ahead. Let me talk about finding my delta x. I kind of assumed it was obvious, but I should not. So the delta x, which is the width of each subinterval, is your b minus a divided by n, which is 4 minus 0 divided by 4, which is just 1. Which is why I was probably making the assumption that it was obvious, because we're going from 0 to 4, we're breaking up into 4 subintervals, they're each going to have a length of, or a width of 1. So each rectangle is going to have a width of 1. And if we're using right endpoints to find the height, it's not too terrible. It's going to be base of 1 times height of f of 1 plus base of 1 times height of f of 2 plus base of 1 times height of f of 3 plus base of 1 times height of f of 4. Usually, when the width is the same for each rectangle, we factor it out. So you would normally write this as 1 times f of 1 plus f of 2 plus f of 3 plus f of 4. Which is going to end up being 1 times the f of 1 is 4, f of 2 is 10 minus 4, f of 3 is 15 minus 9, and f of 4 is 20 minus 16. which ends up being 20. Okay, let's draw the picture because it's kind of nice to see. So this is just a downward opening parabola. It happens to have its vertex when x is equal to 2.5. Let me make the y-axis here. Try to draw it somewhat nicely. That's not right, James. So already blowing it. There we go. 4, 6, 6. It's kind of like this. And then we continue down this way. And what we've done is we've used right endpoints. So we've calculated the area of this rectangle and this rectangle and this rectangle and this rectangle. So that's our estimate there. And even though it's not 100, in fact, no, I don't want to even make a guess at it. I was going to say it looked like it could be an underestimate, but I don't actually know. I think it might be an overestimate. So what I want to stress here is we didn't need this picture to find the estimate using right endpoints. You can just take your interval, break it up into the appropriate number of sections. Now, I personally find it easier to draw the x-axis at least, because it makes it easier for me to see what the breakpoints are. This is a relatively straightforward example, but if I said, use 6 intervals instead of 4, then we'd be breaking up 4 by, we do 4 divided by 6, and do like 0 to 2/3, and 2/3 to 4/3, and 4/3 to 6/3. So I find it helpful to at least draw the x-axis. Let's talk about what left endpoint is going to look like. Yeah, we can fit in left endpoints. So do left endpoints here. Now I do want to draw the picture, not because we need it, just so you can see it. But before we draw the picture, let's do the calculation. I know it seems kind of backwards, but we can easily do the calculation by saying, well, using left endpoints, the area should be approximately, all the bases are still 1. My left endpoints, instead of 1, 2, 3, and 4, are 0, 1, 2, and 3. So we're going to find f of 0 plus f of 1 plus f of 2 plus f of 3, which is going to be, the f of 0 is 0, f of 1 is 4, f of 2 is 6, f of 3 is 6. So we're getting 16. Let's take a look at the picture. I'm going to try and draw it relatively nicely here. Four, 6. Okay, so it looks like this. And now using left endpoints. So for this first interval, I'm using the left endpoint, which is 0, giving me a height of 0. Never exciting. And then for this second interval from 1 to 2, we're using the left endpoint, which is 1, to get this height here. That has an area of 4. From 2 to 3, we're using the left endpoint here. Let's give this a height of 6. And from 3 to 4, we're using the left endpoint as well, which is giving us that rectangle there. So here's the area we're approximating, or I say, here is our approximation of the area under the curve. And that is probably an underestimate. Okay, so now here's where the difference between left and right and over and under is going to be seen. So, or sorry, not over and under, upper and lower. That's the correct terminology. So let's find the, we typically call the lower sum. So the lower sum is what you get when you take the least function value in each interval. In each subinterval, I should say. So this is where it's good to have the picture because it makes it easier to see. But draw it one more time. And I think I said this last class, but just to make sure I reiterate it, you're always welcome to leave early if you need to leave early, or to come late if you need to come late. I understand you have other classes as well. Don't worry about being on time. It's not a huge deal. So let's see. My parabola looks again like this. Usually I don't spend quite so much time trying to draw it so nicely, but I really want to look good. Okay, here's my points. So if I'm trying to find the lower sum, I'm in this first interval, I'm going to use the left endpoint because that's giving me the lower value, the lowest value. In this second subinterval, I'm going to use the left endpoint because that's giving me the lower value. In this third subinterval, I could actually use the left or the right because they happen to have the same value. Let's just go ahead and use the left. Well, I mean, it's the same, right? But in this fourth subinterval, we're going to use the right endpoint because that's the lower value. So here our lower sum, which we typically write, oh yeah. I feel like there's a different letter to use for lower. So let me go back to the previous picture just a second. Usually when we're using right endpoints and we and 4 subintervals, we typically call this R4. Right endpoints, 4 subintervals. And for left endpoints using 4 subintervals, we usually call this L4. But I feel like we also use L for lower. Yes, yes. And then, yeah. I'll have to write it differently. I'll say lower just because I don't know if the book does something different. So that's going to be equal to, so it's going to be 1 times my first rectangle has a height of f of 0. My second rectangle has a height of f of 1. My third rectangle has a height of f of 2. And my fourth rectangle has a height of f of 4. Which is going to give me 1 times 0 plus 4 plus f of 2 is 6 plus f of 4 is 4. So let's just write the function again. Right, the function is 5x minus x squared. And so that's going to give us 14. You're welcome. I will just say before you leave, I want to say one thing. When you do the upper estimate, which we're about to do, the middle one, you have to use the midpoint of 2 and 3 because that's where the vertex of this parabola happens to be. So it's not, so if you're doing upper or lower, it's not always going to be a left or a right endpoint necessarily. It could be a point in.
That's only for the middle.
That's only, well, it could have been a point somewhere not the middle, right? It could have been anywhere. If we're trying to find the upper, we're just trying to find what gives us the highest function value for each subinterval.
Thank you very
Well, so for the upper sum, as I was just saying, we do the same sort of thing. Draw this picture one final time. What time is it? Oh, we got time. Okay. So 1, 4, 2, 6, 3, 6, 4, 4. There's my parabola looking pretty good. Okay, so now if I want to find the upper sum, well, in this first interval from 0 to 1, the right endpoint is going to give me the highest rectangle. But in the second interval, this right endpoint is going to give me the highest rectangle. But in the third subinterval, it's the midpoint. Happens to be the midpoint because that's where the vertex is. So the vertex of this parabola does occur at x equal to 5 halves. You can do minus b over 2a if you want to figure that out. But at 5 halves or 2.5, that's where we're getting the maximum value of the function in that interval. So we're going to get this rectangle looking like that. And then finally, in the fourth subinterval, we're going to use the left endpoint to get the height, to be the highest. So here our upper sum, using 4 subintervals, would be, again, each rectangle has a, base of 1. Then we're going to have f of 1 for the first height, f of 2 for the second height, f of 5 halves, or 2.5, whichever way you prefer for the third height, and f of 3 for the fourth height. So at the end of it being, let's see, f of 1 is 4, f of 2 is 6, f of 2.5, if you plug in 2.5 here, it's easier to see if you factor out an x. This is x times 5 minus x, and if you plug in 5 halves or 2.5, you get 5 halves times 5 minus 5 halves, which is also 5 halves. And 5 halves times 5 halves is 25 fourths, which is 6 1/4. And then f of 3 is still 6. So I end up with, let's see, 10, 16.25, 22.25. And that's our upper sum, using n equals 4 subintervals. So most of the time in this class, and again, this thing we're doing right now is not a huge portion of what we do in front of it, but we're just building up the machinery so we can talk more accurately about the area under the curve of a function. What I'll say about this is most of the time in this class, an upper sum or a lower sum will probably correspond to either using left or right endpoints, because most of the functions you will look at are either going to be increasing or decreasing. So usually they'll end up being the same, but not always. So I do want you to see, right, that in this example we've picked here, the upper and lower are different than the left and right. Right, so here's our, just for contrast, right? So you can see them all on the same page. Here's our lower, which was area of 14. Here's our upper, which was an area of 22.25. Here's our right endpoint, which was an area of 20. And here's our left endpoint, which is an area of 16. They're all different. So again, upper and lower are kind of a pain in the butt. It's usually much easier to just algorithmically calculate left and right, because you can very easily, once you know what your delta x is, find each subsequent left or right endpoint and plug them into the function and multiply. Okay, let me throw one more example at you. It's almost time to go. But this is what we'll talk about more next time. So next time we will use the following example to talk about the limit definition of the integral. So we want next time to calculate the area under f of x equal to x squared on the interval from 1 to 3, which we are going to write as the integral from 1 to 3 of x squared dx. That is the way we notate area under a curve. And what we're going to start by doing is we're going to start by taking the curve and approximating the area using some number of rectangles. So let's start by approximating using n equal to, you guessed it, 4 rectangles with right endpoints. So without drawing a picture, here's how we would do that. You'd say, okay, well, my delta x is your interval length, 3 minus 1, divided by your number of rectangles, which is 4, or a number of rectangles / number of subintervals. And what we're going to do is say, okay, that's equal to 1/2. And then I like to draw I said I wouldn't draw a picture. I lied. Told them to draw a picture, just a little one. So we're going from 1 to 3, and then each subinterval has a length of 1/2. So the next one is going to be at 1.5 or 3 halves. And the next one's going to be at 2, and then 2.5, which is 5 halves, and then 3. And then each of these right endpoints, those are what we're going to plug in to help us find the area. So the area is going to be approximately R4 right endpoints using 4 subintervals. And the base of each of these rectangles is delta x, which is 1/2. And the height of each rectangle, which we will draw next time, well, the first rectangle is going to have a height of f of 3 halves. And the next rectangle is going to have a height of f of 2. And then the next rectangle is going to have a height of f of 5 halves. And then the next rectangle is going to have a height of f of 3. right? So we're just using the fact that we know that they're the right endpoints to get the heights without even drawing. All right, I should stop there because it's 2:00. We'll definitely, so next time, we're gonna talk more about this example. We're gonna refine it to using 8 rectangles and then maybe even 16 rectangles. And then we'll talk about what we actually need to do to actually calculate and not just approximate the area under the curve. Involves taking a limit. And some other funky formulas that we'll need to talk about too. All right, that's all I got. Have a lovely rest of your day.